All right, example number 3. We have a photoelectric experiment where you have some unknown frequency given, but you are given the stopping potential for that particular experiment. The stopping potential we represent with a V and a subscript S for stopping potential, and that's equal to 1.25 volts. And this is what is required to reduce the current to 0. Let me show you a quick little animation for this. So here's the photoelectric experiment. This is our metal plate here, and we're going to just reduce this to some wavelength or frequency, and we'll just turn on our lamp, and you can see that these are photoelectrons being ejected. Now we're looking for, in this problem, the maximum kinetic energy, so really only want to show the highest energy electron. So you can see these other ones that are not shown anymore, and so we have this little electron that is flying along here. We'll have a few more of those. Now we're looking to reduce this current to 0, so if I reverse the potential and keep reversing until I get to a point of 0 current, this potential here is called the stopping potential. So it's the potential that is required so all of the kinetic energy is lost and they don't quite make it to this collector plate. Okay, in part A we're trying to find the maximum kinetic energy of these photoelectrons. Now you might think, well, if I knew the velocity, I could use like 1/2 mv max squared. I suppose you could look up the mass of an electron, which is 9.11 times 10 to the power of negative 31 kilograms, but we don't know the velocity. So in fact, actually, that's what we're asked to find later on. We're going to be looking for the maximum kinetic energy, but we want to use this stopping potential. So you have to realize that the loss of kinetic energy is equal to the potential energy that was used to reverse the potential. So this was equal to Q times V. V sub S to be specific. And Q in this case, by the way, is equal to the charge on an electron. So this is really E times V sub S. And E is equal to 1.6 times 10 to the power negative 19 joules. Now, you could write your answer in electron volts if you'd like. It would be very easy. It's E times the potential, which is 1.25 volts. So really, the energy is 1.25. Bring over that E to over here, and you'll have electron volts. Or, as shown down here, we have in joules. So you could use the charged electron, which is 1.6 times 10 to the power negative 19 coulombs, and multiply by the voltage, which is 1.25 volts, which is equivalent to a joule per coulomb. And when you multiply these two, you'll get an answer of 2 times 10 to the power of negative 19 joules. Okay, now moving on to part B. We want to find the velocity. Remember, we just earlier stated here that the kinetic energy is equal to 1/2 mv squared. So 1/2 mv squared is equal to this kinetic energy, and we're just going to solve for the maximum velocity, and that would be the square root of the maximum kinetic energy, twice of that, divided by the mass of an electron. And this is a mass of an electron. So let's substitute in here. Now 2 times. Be careful again once again with units. You can't use electron volts here because this is not a unit of joules. Remember that kinetic energy, when we use a mass in kilograms and velocity in meters per second, we need to make sure our energy is in joules. So be careful with that. The energy we just determined was 2 times 10 to the power of negative 19 joules, and then divided by the mass electron, which is 9.11 times 10 to the power of negative 31 kilograms. So it's a square root of all of that. And you get a maximum velocity of 6.63 times 10 to the power of 5 meters per second. And that's it for example 3.